Welcome back. In this video, we are going to talk about the numerical solutions of the heat equation of different boundary conditions. In particular, we are going to walk you through the derivation and see how to apply and incorporate different boundary conditions to, generate a desired numerical solution. Let us begin. So here is our heat equation. As a reminder, we have introduced this equation in one of our previous videos where we are modeling a heat distribution on a thin rod. So this is a one-dimensional heat equation, right? And there are two variables. One is the space variable x and time variable t. We have this thin rod on a coordinate system saying if the x is between 0 and L, and also we can model t from some interval 0 to maybe capital T. The equation is as follows. The first derivative u with respect to t is equal to a constant d squared times uxx for every x between 0 and L. And for this problem, we are enforcing a directionally type boundary condition. And here, for simplicity, we are enforcing the zero boundary condition here. So the idea will work for more general boundary condition, meaning that if here is alpha or beta, the following method will work. But here, for simplicity, we're just using this zero boundary condition. And there's also a unique initial condition that we will need to generate our numerical solution. So in PDE theory, there will be existence and uniqueness theory that will discuss when a solution would exist for PDE with particular boundary values and initial values. And the topic is beyond the scope of our course here, but we'll see in our discussion of the numerical solution of why, at least intuitively, these conditions would guarantee a unique numerical solution. So let us first apply the finite difference scheme that we have discussed earlier. So we are using the forward difference scheme for the time derivative here, and a central difference formula for the second order partial derivative uxx, as we have seen in our previous video. So let us write down these formulas for every point x and t. Okay, so this is the derivative at every location x and t. So for forward difference, if you recall, it will be u of, so since it's a derivative with respect to t, then we fix x, then we have t plus delta t minus u xt divided by delta t, right? So now we have the forward finite difference approximation for ut at xt. And then we can apply the central difference formula for uxx. So we need three values. We have ux plus delta x at time t minus 2 times u, and here is uxt plus u at x minus delta x, right? Then at time t, divided, since it's second order derivative, we have delta x squared. So now let's complete the equation. The equation says ut is equal to d squared times uxx, so this is equal to d squared times uxx. So let us actually do some algebra and form the relation between u, x, t plus delta t with all other terms. So here we have uxt. Let us copy it here. Then plus, we have to multiply this delta t to the right hand side, and then maybe collect this constant as well. So we have d squared, then this delta t divided by delta x squared, then all the other terms. So we have three terms, ux plus delta x t minus 2ux t plus ux minus delta x t. Okay, so now we have the relation between ux at time step t plus delta t with u values at a previous time step. Here are all values at t. The location may be different, but these are all values from a particular time t. So let us actually put a grid in our xt plane. So this is the x-axis, this is the t-axis, and we put a spatial grid, a time grid, and generate a grid in the xt plane. So what we mean by a numerical solution is that eventually by using our PDE and our boundary condition initial condition, we can generate the temperature value U at any particular time, right? So we would like to know, for example, at a particular time t capital K, what are the values in all the locations on the grid. So this is what we mean by a numerical solution. And let us use some shorthand notation. So now we have a grid. Let us denote the U value at some particular point xn and tk as U and k. So n is the index for the space and k is the index for time. So in particular, our x is between 0 and L. So x0 is 0, x1 will be delta x, x2 will be 2 delta x. So the spacing in the space coordinate is delta x. And here t0 will be the time at 0, then t1, so here if we consider time will be t1 will be delta t, then t2 will be 2 times delta t. Okay, so now let us just translate this equation or relation with respect to any time and space to the u values on these grid points. Okay, so with this translation, let's say, so if x is just xn, t is just some grid point tk, so we're at a particular, for example, a particular point x and tk, and then the u value at this point will be u and k. Then this value will be u xn. And since we move forward one time step, then we'll not have tk, but instead of tk plus 1, since this is right. So this is, as we just said, u and k plus 1. And this is equal to u xn tk, which is just u and k. And also, let us, just for simplicity, call this constant lambda. Once we have fixed our time step size and space step size, we'll have this constant, right? So this is plus lambda times u at xn plus delta x, which will be xn plus 1, right, at time tk, minus 2u xn at time tk, then plus u at x minus delta x, which will be the previous grid point on the x-axis, right? So just to use this simpler notation, we're going to have this is equal to UNK plus, this will be UM plus 1K minus, with the parentheses here, 2UNK plus 2UM minus 1K. So what we have derived here, let us just look at the figure. So we are saying that by this equation, this value is determined by these three values. In other words, the u value at a particular time step, say tk plus 1, can be determined by three values at time step tk. So in particular, if we're calculating this value, then we can use these three values and this equation to generate this value. And if we would like to calculate this value, then we can use these three values and this equation. So this is our recursion formula or iteration formula. So the current question is, do we have enough to get, for example, a particular time tk, all the values here? It turns out we do. So we have a so-called initial conditions. So the u value for every x at a particular time t equals 0 is f of x. So these are the values for t equals 0. So we actually have these values by the initial condition. So in particular, we can use this recursion formula to calculate all these points. Right, this point is determined by these three, these points is determined by these three, and all the middle points are determined similarly. So what about the points on the boundary? So these are the points on the boundary. Here is x equals to 0 and t is equal to t0, t1, t2, t3, etc. Right? So in this problem, we're saying that the boundary values are 0. So these values are 0. It's given. These values are 0. So as we just explained, these values can be generated by the recursion formula, and these values are given by the boundary condition. And then what about for the next row, for the next time step, for T2, for example? Again, for this value, using the recursion formula, we can use these three values, right? So this value is known by the boundary condition. These values are already known by the recursion formula, so we can calculate this value. And so are all these values. And then these two values are again given by the boundary condition here. So in summary, we have this recursion formula. We also have u for all time step k at at an f boundary point, which is x0 is equal to 0 for all k, and u at the right boundary points, and the index is n here, the nth point, the n plus 1 point, and for all time k is also 0. So this is for all k, right? And we also have that u for the initial time where t is 0 And for every x here will be f at xn. With these three equation, we can generate u at any grid point. So we can generate un k for any index n and k. For implementation, you can, for example, store the values u and k in a matrix. And you can initialize the matrix with the known values specified by this boundary condition and initial condition. In particular, for example, for the first row, the initial conditions are known, right? So for the time step, initial time step where t is 0, you know the values at x1, the values at x0, x1, the values x2, all the way up to the values at, for example, at n-1 and xn, which is equal to L, right? And you also know the boundary values where at x0 for time step 1, at x0 for time step 2, all the way up to the time step, for example, capital K of your interest at 0. And similarly for the right boundary point, then you have u, u at the boundary point for time step 1, u at right boundary point for time step 2, all the way up to for the particular time step of your interest at this right boundary point. And then you can use your recursion formula here to get this value by these three value, and to get this value by these three value, and then all the values in between. And once you get the second row, you can generate, for example, this value by these three value, and this value by these three value, and all the way up to here, right? So in summary, you can use, for example, two for loops. One is to calculate the values in each row, and then you can move forward into further time step to generate the values in every row. As a side note, there are some conditions that guarantee the stability of the finite difference scheme. And the stability of a finite difference scheme is a desirable property. And in particular, an unstable difference scheme would generate unreasonable or undesirable numerical solutions, and sometimes even generate numerical solutions that will not be convergent to the theoretical solution of the particular PDE problem. So that will be useless, right? So here, usually, we require that the constant d squared times dt dx squared should be less than or equal to 1/2. The discussion of stability is beyond our topic here, but in general, when you implement the finite difference step method and choose a step size for space, you should choose a relatively small step size for the time step delta t as well, and satisfy this condition so that we can have a stable finite difference scheme. Maybe I'll come back to this topic later after our next example. So now we know how to generate a numerical solution for the heat equation with a dirichlet type boundary condition, right? And the method we just discussed does not only work for the zero boundary condition, it can actually for any Dirichlet boundary condition as well. So now let us look at the example when we have Neumann boundary condition. So still we're solving the heat equation for a thin rod, and the rod is between the coordinate 0 and L. And we have talked about this example where if we assume no heat exchange, the appropriate boundary condition is to assume the derivative with respect to the space variable on the nth should be 0. So in particular, the boundary condition here is Ux on the boundary points 0t for all t is 0, and the Ux derivative at the boundary point L for all t is 0. Okay. As a side note, so we're talking about boundary. Here, the thin rod is in the is in the interval 0L. So for interval, the boundary points will just be the endpoints, right? So when we're talking about the boundary for a one-dimensional problem, we're talking about 2 points, which are the endpoints of the interval. So that's a side note for the boundary. And also, we need an initial condition for a unique solution to exist. So what's the difference between this problem and the previous problem? Let us now just write down the previous discretization for the equation itself. Here we're using the same finite difference formula for the ut derivative and the uxx derivative. And then we'll get the same recursion formula. And here is what we call lambda as in the previous problem, right? And we have the same initial condition, so we have some known values just as is the same as in the previous example. So at time t equals 0, we have these values where the time index is 0. For any xn, we have it equals f at these xn's. Okay, but the difference is that we don't have these values explicitly given. Right? We don't have the u values at x equals 0 at all time t. We don't have that. Instead, we have the derivative at the boundary point x equals 0. Right? So we don't have these values. So what can we do to these boundary conditions to estimate these values? One way we can try is to, for example, apply the central difference formula to these boundary conditions. So let us apply it. So here, so here is a summary. We don't know the values. So let us apply the central difference formula to the boundary condition. So for ux, for example, at 0 t for all time t, and central difference here is first order derivative, so we have u at 0, so we have 0 plus delta x at time t minus u 0 minus delta x at time t divided by 2 delta x, right? And the boundary condition says the ux derivative is 0, so we have this is equal to 0. So what we can get is here u at delta x for all time t is equal to u at minus delta x for all time t. Okay, so our domain is the interval, as we just mentioned, interval 0 to L. So this interval. We don't really have, the point at, we don't really have the point minus x in our domain. Right, we minus x, and in particular, if we're using the right point, then we will actually need xn plus delta x. So we also do not have the point xn plus 1 or the point x minus 1. But let us just, for now, pretend we have a fictional grid to the left and to the right of our interval. And then, using this equation we just obtained by discretizing the boundary condition, we can actually estimate this value. Recall that by this iteration formula, we're saying that un k plus 1 is determined by these three values. So if these three values are determined, then we can use this iteration formula to generate this value, right? And we know that this value is given, this value is determined by this value using this boundary condition, right? So this is exactly u at delta x is the, delta x is just x1. Then for all time t, let's say we're applying it to any tk, then we have u, for the minus 1, the fictional grid point for any time step tk. So in particular here, we have enforced the equation that this value is equal to this value, this value is equal to this value, this value is equal to this value. Okay, so let me label it here. So this is u for x1 at time step 1. This is u for x1 at time step 2, right? And for example, maybe this is u for x1 at time step k. This is u for x minus 1 at time step k. So we're saying that these two values are the same. We're saying that these two values are same. These two values are the same. These two values are the same. Okay. So once we have this value, all the other values can be calculated by the recursion formula as before. For example, this value can be calculated by these three values, and this value can be calculated by these three values. And all the way to here, right? This value can be calculated by these three values. And then, what about this value? Remember, we have also the boundary condition at x equals L. So in particular, using the same idea, ux L at t and central difference formula, we can actually derive that u at, for example, L plus delta xt is equal to u L minus delta xt, which using our notation for the discrete point, then we have u m minus 1 for all time step k is equal to u here, sorry, should be m plus 1, m minus 1 for time step k. So it is totally symmetric. We're saying that this value is equal to this value, and this value is equal to this value. So like in the left boundary point, we can generate this value directly by this value. And once we have these three values, we can use this recursion formula to get this value by these three values. And now we have just explained how we can apply all the values on the second row of the grid points. And we can do it again, right? We can generate all the values in between using a recursion formula. And once we have this value, we can use the boundary condition, not exactly the boundary condition, but central difference formula applied to the boundary condition to generate this value. And then this, so this value can already be generated by the recursion formula. So we can generate all the values in between here. And for the next row, we can do it again. So in summary, we have this recursion formula unk plus 1 is equal to unk plus lambda un plus 1k minus 2 unk plus minus 1k, and we have u for time step 0, n is equal to f of xn, and we have u minus 1 for ok is equal to u1 for ok, and for the other boundary point we have u m minus 1k is equal to u m plus 1k. With these conditions or values, we can actually generate any u and k. So let us look at the implementation in MATLAB. So we can again put it in a matrix, right? And we have these values, the initial condition u0, 0, u0, 1, u0, 2, un minus 1, 0, un 0, right? And then by this condition, we can plug in to here to generate the formula for the boundary points. Okay, so let us do that. So since we only need the formula for the boundary points, which is we only need it for xn equals to x0, so n is 0. K plus 1 is u0 k plus lambda u1 k minus 2 u0 k u minus 1k. So we're applying the recursion formula to n equals 0 to the left boundary point. Okay, so we know that by this condition we just obtained that u1k is equal to u minus 1k. So this fictional, the value on this fictional grid point is equal to, one value actually on our discrete grid. So if we plug in then this is 2 times u1k minus 2u0k, right? So what we're doing is, although we don't know the boundary value explicitly as in the previous example, we can generate, for example, if we would like u02, u01 for the next time step, t1 will be u01 plus lambda 2u10 minus 2u00. So to generate u1, excuse me, u and next time step for the boundary point, we can use actually these two values, right? u0, u01 and u00. So we don't actually have the fiction point here. And also, you can generate the exact same same kind of equation for the right boundary point. So you can generate actually the point un1 by these two values using this kind of formula. And for the other values, you can use the exact recursion formula. For example, this value will be generated by these three values, right? So if you choose this implementation, you can use this formula for boundary points, and then the same recursion formula here for all the other points. And once you have the second row, you can, do the same thing and progress. Okay, so if you do not like to, really have a different formula, but apply the same formula again and again, what you can do is, your implementation, you can actually choose a larger matrix to store the fictional grid. So instead of storing the initial value, you can store the value at the fictional grid, u-1 at time 0, u0 at time 0, u1 at time 0, u2 at time 0, all the way, un-1 times 0, un times 0, un plus 1 at time 0. So this corresponds to the value at x equals 0, and this corresponds to the value at x equals to L, and this is a fictional point, and this is a fictional point. What you can do is determine this value by this value, determine this value by this value using this equation, right? And then you can just apply the recursion formula for all the values from here to here. For example, for the second row, when you are determining u at x0 for the next time step, you can use these three values, right? We just used three values in the previous time step. We use three values at the previous time step, right? So similarly, you can determine u at x1 for the next time step by these three values, and all the way to un time step 1. And then once you have all these values, you can obtain the fictional value by just using these two equations. And so this value will be equal to this value. This value will be equal to this value. So you have u n plus 1, 1. And now you have the second row and you can progress. So here, you can do the same iteration, but by directly applying the boundary condition here and here, and the same recursion formula, which is here, without specifying the particular recursion formula for the boundary points like you do here. So you can choose either implementation. And now I think you know how to use for loops, for example, in MATLAB to obtain a numerical solution for any discrete grid, right? So again, we need to guarantee stability, and the stability is the same. We need to have delta t less or equal to 2d squared delta x squared. So this is the same stability with a different form, maybe as here. In other words, we cannot choose a very small spacing or step size for the space coordinate without choosing a very small time step. This would guarantee that when your step size goes to 0, getting smaller and smaller, in other words, the solution, numerical solution, will not blow up or goes to or become unbounded. So when you have your diffusion constant and choose some kind of step size, you have to take into account of some time step value that satisfies this equation. But of course, you don't want a very, very small time step, because that will be computationally expensive. So you would like stability and also efficiency. And in particular, this will guarantee stability by some theory actually developed by von Neumann. So this concludes our discussion of the numerical solution of heat equation with different boundary conditions. And yeah, and now you're ready to solve a more general heat equation with other directional boundary or Neumann boundary condition, or even mixed boundary conditions, which you can actually combine the techniques in this example and this example. So thank you.